All right. So again, I'm going to solve the same problem, but this time with a better way. So the problem is this. So I have a point on the surface of the Earth. Let's say that that distance is equal to the radius of the Earth. We have the gravity in here, and then I have another point somewhere in here where the gravity has a different value. So that other point has a distance h. It has an altitude h above the ground. And so as a result, g has the value of gme divided by re squared. And g prime is, right? We would like to find out how these two quantities differ from each other. So that's basically this value in here. So obviously we need to find g minus g prime. In any case, so what we do is, what's important in here is that what makes g prime different from g is basically that term. So it's this h in here, which is added to the denominator, whatever, is the one that makes the difference. As a result, I can start from this. So one of the nice techniques in here is to make the inside dimensionless in here, this expression dimensionless. So as a result, I can write g prime as g times me divided by, I take re out, so that's re squared times 1 plus h divided by re squared. Okay. So there are these two simplifications in here. So first, we have this thing in here that already has a name. I know that I can replace this with with gravity. All right, let me undo all of this and write this thing down like that. So g prime can be written as the gravity divided by 1 plus h divided by re squared, right? That's one simplification in here, because I would like to find a difference between g prime and g. And I finally have an expression where only they are in here. And I only have an expression where this small dimensionless quantity is in here. So this h over re is basically much smaller than 1, and it is dimensionless. Okay. So in any case, so what we can do is we can expand this by this binomial expansion, but probably it is better to do it by just moving it to the numerator. So as a result, I'm just going to write it down like that. This is h over re to the power minus 2. Okay. Why did I move it to the numerator? Because it's easier to handle it like this, right? Because I would like to find g prime minus g, and I can handle it in that way better. So in any case, I have talked about this thing before. I can write this expression as 1 plus the power multiplied with h over re, and then plus this power minus 1 divided by 2 factorial multiplied with h over re squared, and so on. Okay. In any case, let me just shift right or shift below, shift, whatever. Yeah, let me write this thing down in here. So that's the binomial expansion. Okay, so it says that 1 plus x to the power n is equal to 1 plus n times x plus n times n minus 1 over 2 factorial times x squared. Let's continue, plus n minus 1, n minus 2 divided by 3 factorial x cubed, and so on. That's the binomial expansion that you know. What I said is that this is valid not only for positive integers, but also for fractional numbers, negative integers as well. So valid for all real n values. So as a result, for example, I can write 1 plus square root of 1 plus x, for example, in the same way. So that's like 1 plus x 1/2 of x plus 1/2 minus 1/2. Yeah, whatever. I mean, I can do this expansion in here. So what's important for us is that if x is small, let's say it like this. If x is much smaller than 1, then that means 1 plus x to the power n can be replaced with 1 plus n times x. I have shown you this when I was talking about derivatives, right? Now I'm reminding you this. So as a result, I can write like 1 plus x, for example, approximately as 1 plus x over 2. I can write 1 plus x to the power minus 2 as 1 minus 2x, okay? Or I don't know, I mean, 1 over 1 plus x, for example, which is 1 plus x to the power minus 1. So that can be written as 1 minus x. I mean, there are these kind of expressions that we are going to meet a lot in physics. And so as a result, by using the first term of the binomial expansion, right, provided that this is the case, of course, that's important. In that case, I can use this, this approximation in here. Okay, so that's basically the, first term is 1. It's the second term in the binomial expansion. Okay, so in here too, I'm doing the same thing. So that's irrelevant in here because I know that h over re is very small, like it's like 10 to the minus 6, 1 in a million. So that means this is much, much smaller than the first term. And so as a result, this is irrelevant, okay? So what I do is I just drop this part and then replace this equality in here with an approximation, okay? So this is approximately equal to g times 1 minus 2h over re. Okay, this is faster because you are using an approximation, the binomial approximation in a systematic way, okay? So that means g prime minus g is equal to minus, g times 2 times h over re. Obviously, this is negative as we expected. So delta g, g minus g prime is g times 2h divided by re. It's the same expression. But I mean, you reach it in a faster way. And somehow you have also read out these quantities with the dimensions. Yeah, whatever. I mean, I did the simplification at the beginning in here. So I did it at the first stage in here, okay? So here, however, I did it like, when did I do this? I did it somewhere in here after making this approximation where h goes to 0. So this is kind of complicated, this method is, because you have to decide on in which places you have to neglect the small quantity and in which places you shouldn't. So this actually does the same thing, but in a more systematic way. Okay, so in both cases, there are these higher order terms. By neglecting these extra things, you're essentially eliminating these higher order terms, but you obtain this one correctly in there. Okay, so in any case, at the altitude of the International Space Station, basically H is 227 kilometers. Yeah, the value was changing actually. Yeah, I can actually refresh this page and probably you're going to read a different figure in here because the altitude changes continuously. Yeah, let's see the new altitude now. Yeah, this time like it's like 425, whatever. The thing that we are going to compute is going to be actually some errors as well. So this is like 6,400 kilometers. So that means h over re is, this time it's not much smaller than the than 1, but it is small. Yeah, let's just write this thing down. That's hard to calculate. So let me just do it like this. 3 divided by 3200. I think I'm going to put a point in here and then point in here. So that's going to be like 1/32. So that means 0.03. Sorry, this is 427. Sorry. Extremely sorry. 427. So that's like, if I divide by 4, then it's like 1600. And it's going to be 100 and something like 8 or something, right? Or 9. So that's going to be 1/16. What's 1/16? 0.06, right? Yeah. Which means twice that. I mean, G minus G prime would be like G multiplied with 2H over RE. So that's going to be 0.12 G. So that's going to be about like 1.2 meters per second squared. This is approximate in any case. So probably from the neglected terms, we might have some corrections as well. So if G is like 9.8 meters per second squared, then G prime would be like 8.6 meters per second squared. This Wolfram alpha thing is somewhat nice. Probably I can also get the value of the gravity at the location of ISS. Sorry, let me just try this because I mean, this is some kind of an computation machine with some kind of an intelligence. So let me write gravity at the location of ISS. So it is supposed to understand what I'm asking, but sometimes you don't get lucky, right? All right, that's the local gravity at the Earth, but there's no ISS in here. Probably there's some kind of an airport in here. Let's see. International Space Station. It's just a second try. So I don't know if you can see this. No, I don't see any gravity in here. All right, so I don't have luck today. All right, so in any case, so the question in here is that, I mean, they're not in, well, they are in space, obviously, but they are not in a part of the space where there's no gravity. There's gravity there. And the question is why they are feeling this weightlessness. This is just a figurative question. And I know that I have explained this before, but that's kind of striking because a lot of people assume when they see these like movies and videos of astronauts flying around, they kind of assume that there's no gravity there. There is gravity there. And it's not very much different than the gravity at the Earth. So probably nobody would even notice the difference between the gravity in here and gravity there. You wouldn't notice if you experience it directly. In any case, somehow they don't feel the gravity there, right? And we know the reason for this. Well, the reason is that the International Space Station is in free fall. So it didn't matter whether the gravity in there is like is 9.8 or 10,000 times bigger than this. It doesn't matter actually. They wouldn't feel the value of the gravity because they are in free fall. So relative to the International Space Station, somehow it appears that there's no gravity at all. Okay, so this comes to this other question that I posed somewhat paused before. So let's say it like this. Mass, this concept appears in two different laws of nature. There's a question in here, but I'm going to ask the question. So that's Newton's second law. So it says that the net force is equal to mass times acceleration. So that's the Newton's second law. And the other one is the gravitational force expression. In the gravitational force expression, so that's the Newton's law of gravity. Okay. So basically in here, mass is basically a measure of inertia. I have said this before, it basically measures how large an inertia an object has, right? Bigger inertia means it's bigger reluctance to motion. So as a result, it is harder to accelerate such an object. Bigger reluctance to change in velocity, let's say it like this, because inertia is the property that it keeps the same velocity. So if you want to change this, inertia is the reluctance to change the velocity. So mass is a measure of inertia. Here, however, mass is a coupling constant. It's called a coupling constant because that's the term that physicists use to express this. Basically, it determines how it couples, how strongly it couples, an object couples with this gravitational force. Let me write it down like this. Determines how strongly an object interacts with other objects through gravitational force. Okay, so there's a concept called gravitational force. So some objects, well, all of the objects can apply this force, but some objects are able to apply bigger forces, bigger gravitational forces. So as a result, mass is basically is proportional to their ability to apply these gravitational forces. So bigger mass means that they can apply larger gravitational forces. Okay, so as a result, the quantity appears with these two different functions in these two different laws. And the question is why? Right, why is kind of a dangerous question. So it kind of implies that there's some kind of a purpose in here. And that's not really what I mean. The question is like, is this a coincidence, right? Why is it that the same quantity somehow appears in these two different places? So is it a coincidence that that mass appears in these two different laws of motion? Okay. So that's an important question. So in any case, I mean, if it is the same, the idea is this: if the mass appears in these two different places, if the same mass appears in these two different places, there has to be a reason for it, right? Right. So there cannot be a coincidence. Basically, there are no coincidences in nature. There has to be a reason for it. Okay. Physicist asks how. Yeah, that's the question. So I'm really asking, how is it that these two laws somehow contain the same quantity in there, right? So, I mean, probably no, but in any case, I mean, let's just try to explain this. So one approach is to do this. So perhaps, okay, let's say each object has two different properties, two different mass properties. Okay, so one is called the inertial mass. I'm going to show it like this. So that's called inertial mass. This is the one that appears in here in Newton's second law. That's F net, right? And the other one is called the gravitational mass. And this appears in the Newton's law of gravity. So that's like mg1 multiplied with. So in the law of gravity, these two masses actually appear. Okay. So as a result, probably, perhaps this is the situation. So as a result, this is one question that is worth investigating, right? So perhaps that we don't have a single mass property, but we have two different mass properties. Somehow, since we didn't know the difference between them, we called each one as mass. So probably if they are different, then we should invent a new term for the other one. But right now, I'm just going to call them as like inertial mass and gravitational mass. When we tried to find the mass in previous chapters, we said that it's a measure of inertia. Why we choose the first explanation, but not the second? No, I didn't choose anything in here. Okay. So, I mean, if it is the same mass, then therefore this, I mean, if it is the same quantity, therefore the same quantity appears as like with these two different roles, as a measure of inertia and as a coupling constant for gravitational force. Okay, but probably they are different. They are not the same. So as a result, probably there's some kind of a difference. So suppose that this is the case, right? Let's suppose that this is the case, all right? So in that case, this is what's going to happen. So let's say that this is the Earth, right? And I have an object in free fall, right? Object in free fall. Okay, let's see, what do we have in here? So this object has some kind of an inertial mass, and it also has a gravitational mass, right? And let's see what the acceleration is. So I know that the net force acting on it is equal to its gravitational mass multiplied with gravity. And I know that because of Newton's second law, that's inertial mass times its acceleration. And so therefore, the acceleration would be equal to mass of the gravity divided by the mass of the inertia times the gravitational acceleration. So it's basically the ratio between these two objects. Okay, so in any case, so here the question is something like this, right? So question, do all objects, yes, let me ask it like this, have the same mg divided by mi ratio? Okay, so that's the first question that we ask right now. Right, let's suppose that there's this gravitational mass and the inertial mass, and they are different. So the first question is this: do all objects have the same ratio? All right, let's say it like this: if yes, right, then all objects in free fall have the same acceleration. Right, let me write same in here, acceleration, if yes. If no, then there are some objects which are going to have different free fall accelerations, right? So as a result, this is a question that's worth investigating experimentally too, right? But let me just say something more about this. So in that case, what happens is that if that's the case, let's just call this constant some kind of a number. So I don't know, I mean, let's call this like B, for example. So this is like mg divided by mi, okay? In any case, so it's the same for all objects. Right, so in that case, what happens is that in the Newton's law of gravity in here, I can easily write this thing down, mg2 divided by r squared. Let's see, all mg's can be written as b times the inertial mass of each object. And so as a result, this expression becomes like g times b squared, the inertial mass and inertial mass in here, and divided by r squared. So as a result, by just redefining the gravitational constant, I can basically use, redefine the gravitational mass as equal to the inertial mass, right? So in any case, so we can redefine so that mg is equal to mi, right? And that basically corresponds to being b equals 1. Okay, so I want to actually make sure that you understand all of them. So do all objects have the same ratio? So that's the question that we are asking. We're not asking whether this ratio is 1 for all objects, but they are essentially the same questions in here, because if this ratio is the same, then by just redefining one of the masses, I can define them to be the same, exactly the same to each other. And so therefore I can define the ratios to be equal to 1. All I need to do is to replace the definition of the this gravitational constant in here. So we're not interested in the value of this one, the precise value. So we don't adjust this value to anything. We just measure it. All right. So as a result, we first fix our definition of the masses, and then we measure it. And that's basically what we do. Okay. So if that's the case, that means all objects have the same ratio for the gravitational mass to inertial mass ratio. Then this is the case that I can define both of these masses to be the same, so I don't use two different definitions. And then we come back to the square one. So as a result, yeah, I mean, it's the same mass that appears in the two laws of nature, right? So therefore, we will say that same mass appears in both laws of nature. Okay. I don't know if you're confused by this. So that's the confusing part that might really be confusing. Okay, let's come back to this. Again, F equals ma. And the gravitational force is equal to G times, right? In one case, of course, I need two masses, but it's just a trivial replacement. The other equation is this. So if that's the case, then it's the same mass that appears in these two equations. But remember this. When I discussed the Newton's second law, I said something about the definition of the force. How do we define the force? And at some point I said that, well, we cannot define it before knowing anything. So that's the first law that we will see. And so before seeing that law, there's no way to define what a force is. So basically we use this law to define and to measure forces, right? So all of it basically contains some kind of an arbitrary definition of the mass of an object. And by using this definition, we also have a definition for the amount of the force. So we use the Newton unit based on the kilogram unit. Okay. By redefining these units, by redefining kilogram unit to be something else, perhaps. Okay. I can redefine the Newton units in such a way that this equation is still valid, and there won't be any problem in here. But this constant is going to change in that case. Okay. So that's basically what I mean. So by redefining kilogram units, we can change the value of the gravitational constant G. That's what I mean. It basically depends on the definition of the kilogram unit. So how do we define kilogram unit? Do you remember? Let me remind you, it's basically taken as 1 gram is taken as the mass of water in 1 centimeter cube volume, but at a certain temperature, but it has to be pure water and things like that, right? It's basically some kind of an arbitrary thing. So you have to use some kind of material in here. It's a particular material, water, but there's also a distance involved in here. How is the 1 centimeter is defined, or 1 meter is defined? After the French Revolution, the Frenchmen actually started with this. They somehow tried to look at this, everything's in a scientific way. And so as a result, they redefine these units in a way that kind of is independent of, I think, the human nature. So they actually took the size of the Earth. The circumference is something, so they just take the 1/4 of the circumference. So that's basically the distance from the pole to the equator. And they divide this to 1 million. Is it 1 million or 10 million? Yeah, whatever. I mean, they actually took this as 1 meter, right? In any case, whatever it is, right? These units are defined, the lengths are defined, and the mass is defined. By defining them in a different way, we can define them and define these units in a different way. Okay? So mass would be defined in a different way. The acceleration would be, right? Its numerical value is going to change. But since the unit of the force is dependent on the unit of the kilogram, Newton's second law is not going to change in form if I do a redefinition of the units. But this is going to change. Okay? So as a result, the value of the gravity is actually, it's not a, I mean, so that capital G, this is the universal constant of gravitation. This value is dependent on how we define the units. It's not a fundamental constant of nature. Because, I don't know, some other people who use different units, this G has a different value, numerical value. So for example, it is customary in particle physics. I mean, some particle physicists do this. They just define the masses in such a way that this constant is equal to 1. I mean, it is customary for some physicists basically to do these kind of changes, all right? So as a result, that's the significance of that thing in here. The universal constant of gravitation, right? It somehow adjusts the fact that we define the mass by some arbitrary means. Yeah, we just put it there to make the formula correctly, right? Okay, so there's this kind of an issue in here. Usually when people talk about the universal constants of nature, they don't talk about these kind of constants that have some kind of a unit, like the speed of light, for example, right? This also has some kind of a unit as well. they actually talk about things that do not have any dimension. So these kind of constants, dimensionless constants, they have the same value no matter how you define these kilogram units and meter units and things like that, okay? And there are some certain constants that you can actually form with these kind of things. But when you take some kind of particle physics, you are going to learn these kind of dimensionless constants later. But right now it is hard for me to explain what these things are. In any case, so whatever, I mean, that's one of the things. So in any case, if all objects have the same ratio, then that basically corresponds to the case where the gravitational mass and inertial mass, they are one and they are the same thing, right? I can then go to this case. But if no, right? For example, let's say a neutron and a proton might have different mg divided by mi ratios. Okay, so a neutron and a proton, sorry about this, proton has a symbol P, and perhaps an electron too. I mean, some particles, some elementary particles might have different ratios for this gravitational mass to inertial mass, right? So that means, let's say it like this, the free fall acceleration of these objects is basically equal to the ratio of these two masses times g, right? Because of that, therefore, if that's the case, neutron and proton will have different free fall accelerations. Free fall accelerations. Different, right? If no, then they are different. So they are going to fall with different accelerations. Perhaps that can be measured. So in any case, some of the materials like, I mean, carbon-12, for example, have equal numbers of proton and neutrons, but iron might have, it's like 26, but I don't remember, this one is like 56 or something like that. I don't actually remember this. So different matter has different atoms have different ratios of protons and neutrons. And so as a result, all of these different atoms will have different ratios. So let's say it like this. So that means different materials will have different free fall accelerations. Okay. And different isotopes, yes. So in any case, so the essential idea in here is that you can measure this if they are different, then this can be measured, right? All you need to do is to somehow you have to produce some kind of a vacuum environment, have an iron ball and have a carbon ball, let them do this free fall motion, measure their accelerations and try to just compute, I mean, try to measure them as accurately as possible and try to find the difference between them. Okay, can be measured. Okay, problem is, right, if they are different, we don't know how different they are. Like, are they different in like 1 part in a million? Or are they different in 1 part in a billion, right? If they are different in 1 part in a billion, then we have to do a very accurate measurement to be able to measure that difference. And so as a result, I mean, at first, in the first experiments, perhaps we cannot measure it. We cannot find a difference. But in any case, I mean, we can actually And this is one of the experiments that we can do. So that's the Ötvös experiment, actually. That's basically trying to, I mean, you can actually look at the Wikipedia. This is the Wikipedia page, right? This is actually remained from the times where the Wikipedia was forbidden in our country. In any case, so I was using Wikiband at that time. But in any case, it's basically an experiment that tries to determine if different particles have different gravitational to inertial mass ratios. All right. What happens is that they have done this experiment in the past, and apparently Newton has done this. The earliest experiments were done by Isaac Newton. But in any case, the modern experiments are also done. They can measure this, they try to measure this with some certain accuracy, but up to that point today, nobody was able to measure any measurable difference in here. So apparently with this high accuracy, I don't know the accuracy in here. Yeah, it's like 10 to the minus 15, all right? With this accuracy, it appears that all particles, all elementary particles have the same gravitational mass to inertial mass ratio, okay? If they are exactly the same, then we cannot actually check this, verify this experimentally. Unfortunately, we cannot do this. If they are different, then we can experimentally measure the difference. But if they are the same, then we cannot experimentally test that they are the same. So there is this kind of an imbalance between these two situations. In any case, so whatever, I mean, so it appears that this is not the case, all right? So it appears that they are not different, so that we don't have this kind of a situation. All objects have the same free fall acceleration, it appears so. So it appears that, therefore, we have this situation in here. So it is the same quantity that appears in two different laws of nature. And since it cannot be a coincidence, it has to be explained. It has to be explained, right? There has to be some explanation of why this has to be so. Okay, so I kind of give you some kind of an idea of what might be the explanation, because I said that like this inertial, sorry, fictitious force has the same form as the gravitational force. So basically the explanation is something like that. In any case, Einstein was the one that used this thing in his arguments, but this kind of a weak form of equivalence principle. So the explanation is basically the explanation of the gravity. Explanation is called the general relativity. So that's our modern theory of gravity. Okay. So it's something quite different from us, from our theory in here. So here we are treating the gravity as a force, but in general relativity, it doesn't treat it as a force. It's basically tries to explain gravity as a result of some space-time geometry or something like that, all right? It's something that we cannot explain in here, unfortunately. But in any case, there is an explanation. That's just keep this in mind. This is the reason why we do this discussion, why there might be like gravitational mass and inertial mass. Somehow the fact that these two masses are the same is significant. And it is only significant because it kind of explains, kind of supports this, this theory of general relativity might be the correct theory of the gravity. Okay, right? It is only for that reason why this is important, and that's the reason why people try to improve upon this Ötvös experiment, they try to improve this accuracy actually. Okay, let me stop here. So that's the complicated part. I know that some of you are confused, but in any case, I mean, you're going to meet this discussion at some point. So basically, this is, I wanted to cover this discussion at the correct place in here.